Okay, thanks everyone for coming to this week's QFT and Physical Mathematics seminar. We're delighted to have Mario DeMarco from UL Brussels, and he's going to tell us about 5D conformal matter.
Thank you very much, Robert, and thank you very much for the invitation. I'm super happy to be here. And okay, so I'm going to talk about a certain, say, research line that we are developing with Michele Del Zotto, Andrea San Giovanni, Michele Graffeo, and Julius Grimminger. And actually, two papers that are the one in blue and red. One of them is out today. Contains main part of the result that I will talk about today, but there is also some follow-up that I will quickly announce just as an idea at the end of the talk. So let me show you what is the outline of today's talk. So I will start with presenting the problem of classification of 5D n equal to 1 superconformal field theory. I will give some motivation, and also I will give the general strategy that we use to attach such problem, namely the use of M-theory geometric engineering. Then there will be a second part of the talk that will be more technical, in which I more technically discuss the case of a certain specific class of such conformal field theories that are called atoms in this talk. I will briefly explain why. Then I will talk about another class of such CFTs that are called molecules, and I will highlight some dualities between mass deformation of the CFTs that we are studying. And in both these two sections, I will actually also comment on the dynamics, on the Pick-Weber realization, and on the magnetic quiver of such theories. And I will briefly conclude then by talking a bit about this forthcoming paper with Michele Zotto, Michele Graffeo, and Andrea San Giovanni. And I also will say what are the conclusions and what are the possible future directions that we are investigating. Okay. Very good. So first of all, what is the problem that you want to touch? In general, one will be very happy to classify quantum field theories. But this problem is for sure daunting as it is. And so a smart idea to begin with is trying to classify the possible fixed point of RG flow, namely conformal field theory. But again, this is just a title because, again, this problem is extremely difficult, in particular in higher dimensions. And so one can introduce a finely tuned assumptions that make the problem interesting, despite being not impossible to solve. Namely, we introduce some assumption that we require that our CFT is actually a supersymmetric CFT, namely SCFTs from now on. And apparently, the Riemann supersymmetry that we have to introduce in order to have not a too trivial problem, but also not too difficult to solve, is 8 supercharges. An example of this is the 6-dimensional case. So to begin with, without string theory, for a long time it was believed that there were no such CFTs in dimension higher than 4, or at least they were very extremely mysterious and difficult to study. But well, if one introduces instead 16 supercharges, namely the well-known 2,0 algebra, supersymmetry algebra, then the problem of the classification is kind of trivial, in the sense that these theories are labeled by Adili algebras. The problem becomes instead way much more interesting if we reduce the amount of supersymmetry. We have just two options in this case, and we pick the 1,0 algebra. And the problem was very nicely solved by F-theory constructions that basically managed to produce solution, F-theory construction in F-theory for almost all, if not all, the bottom-up consistent 6D 1,0 theories. And the strategy in order to find such classification was went under the name of 6D conformal matter. So now that I describe what is the problem that you want to study, let me give some motivation why we should even care. So first of all, higher dimensional superconformal field theories unveil properties and organize lower dimensional superconformal field theories via compactification. And for example, as we will see today, we have the possibility of guessing data as, for example, the X-branch feature magnetic quiver in 5D, and then make some statement also on lower dimensional field theories, namely in 4D. But, and this is one bit of the motivation for classifying higher dimensional superconformal field theories. But then there is an extremely interesting question that descends from various conjectures in the past years, two conjectures, and it goes can be phrased as follows. It is do all 5D superconformal field theory descend from circle reduction, from compactification on a circle of a 6D superconformal field theory or of a 6D little string theory? And so, in some sense, a good reason for doing trying to study such class of theory in namely the 5D conformal matter rather than the 6D conformal matter is that we are looking for exotics. Exotics are theories in this setup that are peculiar of 5D and can be realized just in 5 dimension and more difficult to be realized in 6 dimension. An example of them, for example, a feature that we will be happy to find and reproduce is the presence of some flavor group containing at least this kind of factor, so 2k to the cube or even to the 4, and we call them trinions and tetrons. So like finding such theories produce many possible questions on this conjecture and on the higher dimensional completion of 5D superconformal field theories. Okay, so today I'm going to talk about two issues that we addressed in the two works that I presented at the very beginning. The first one is try to study and extract some dynamics features from this 5D superconformal field theory that from now I'm going to call conformal matter theories. And this is the content of the paper of today. Okay. And then at the end, I will briefly anticipate some results that we are finding with Michele Lezzotto, Michele Graffeo, and Andrea San Giovanni on these trinions and tetrons. Okay. So the strategy of 6D conformal matter that we are going to reproduce also in 5D is somehow can be thought as having learned a good lesson from Lagrangian superconformal, so Lagrangian supersymmetric quantum field theory. So in this slide, I'm not assuming conformality. But a nice bit that I want to highlight of these theories is that they can be compactly described in terms of a graph that we know it's called quiver. And the nice bit is that supersymmetry is so constraining in this case that this kind of graphs of the quiver where nodes correspond to gauge and flavor group and edges correspond to Lagrangian fundamentals, the supersymmetry is so constraining and rigid that just this graph uniquely fixes the Lagrangian of the theory, and so also the local definition of the theory. And then to begin with, the quiver actually can have arbitrary complicated shapes, but indeed they share a common deep and simple structure in the sense that they can all be decomposed in fundamental building blocks. What are these building blocks and what I mean by these? Well, I call these building block atoms for an example of a quiver gauge theory of type SU. Oh, sorry, this is a typo. This edge should be single. For quivers of type SU, we can think of as the indecomposable building block these Lagrangian bifundamental. For example, in this setup, hypermultiplied in the bifundamental of SUN times SUM. And now we realize that actually the most general quiver can be obtained by starting from a bunch of such atomic building block and gauging diagonal subgroups, for example, of these flavor symmetry reds. And for sure, you can keep going on and reproduce the most complicated shape of the quiver that you want. So we would like to reproduce this nice structure in the sense of having a large class of theories that we can graphically describe via quiver or a generalization of it. And in particular, this implies that you can think of all these objects as being obtained by simpler objects that are called atoms, and that we can engage together to form the more complicated objects that are called molecules instead, with a chemical analogy. So, okay, this story was true for Lagrangian field theory. And so the natural question is that can be such a nice structure being exported to non-Lagrangian theories? Particularly in 5D, we have to completely forget about Lagrangian because Lagrangian will never be conformal. They can be at most the deformation of conformal fixed points. And so, in some sense, we can also turn the question around, and one really would like to explore the non-Lagrangian setup starting from the Lagrangian one. And so, a good question to explore it wisely is the following. What is equivalent to ask ourselves what are the features that we would like a quiver to have, but that we cannot produce within the Lagrangian setup. Some of these features are, for example, see, yes, this is the reason why it was a typo. I will denote from now on, apart from the old slide, interacting CFTs with this double edge. And so the thing that we want to reproduce is, for example, gauge nodes and flavor nodes of type E, or also type D for sufficiently big D. And on top of that, we would like also to reproduce some kind of trivalent nodes, similar to those, for example, of class S setup. And so trying to produce such kind of indecomposable building blocks and reaching the possible choices of atoms naturally led us outside the Lagrangian regime, the Lagrangian setup, and permits us to explore non-Lagrangian CFTs, but with this deep structure in mind. All the superconformal field theory within the class that I'm going to study today will seem very difficult, but can actually be described by a graph, namely a generalization of a quiver. And so they can be decomposed in many indecomposable building blocks that from now on I call atoms, that we can gauge together to form the most general quiver, generalized quiver, that is to be thought as a molecule. Okay. So now, how to have a machinery that produces for me these bifundamentals? Well, a good idea, since F-theory works so well in 6D, is to use M-theory instead, because M-theory on a Calabi-Yau threefold, so if I take M-theory on Minkowski 5 times a Calabi-Yau threefold X, is going to give me a superconformal field theory in 5D. And this superconformal field theory localized by the interaction between the supergravity degrees of freedom and some degrees of freedom that instead are associated to M2 and M2 and M5 branes that becomes massless and light at the singular point of my Calabi-Yau threefold. Something that is rarely considered is that actually Calabi-Yau threefold can have both point-like singularities, like these red dots here, but they can also have non-isolated singularities in codimension 2. And so from now on, I will denote with these lines, solid lines, actually in the picture above, the non-compact lines of singularity of my Calabi-Yau threefold. And these non-compact lines can actually intersect at a single point in the Calabi-Yau threefold, that is the red one. And this is the point that is in codimension, is in complex codimension 3 within the Calabi-Yau threefold, or equivalent is in complex real codimension 4 in the Calabi-Yau threefold, where the 5-dimensional theory actually localizes. Okay. So I'm going to claim that these kinds of setup actually really produce for us what we want, namely the bifundamental superconformal field theory that can be thought as atomic and indecomposable bifundamental with flavor group of type G times G and G an Lie algebra. So why this? Because these non-isolated singularities within a Calabi-Yau threefold must be if I go locally on a generic point, for example, of this blue line, their local threefold will look like C times a surface singularity. But surface singularities, Calabi-Yau surface singularities, are labeled themselves by AD algebras, are the so-called AD singularities or dual singularities, or also known as orbifold of C2 by a subgroup of SU2. But the important thing for us is that they are labeled by AD algebra and using the geometric engineering dictionary, namely looking at the dynamic of M theory nearby these singular lines, the dictionary states that if there are such intersecting lines of dual singularity, we have a flavor symmetry of type G times G, where G is the label of the dual singularity. Okay. Okay, this was for the atoms. Is there any questions so far? This is for sure just the idea of what I'm going to explain. Then I will get more. I will go slower and more technical in the next slides. Okay. If it is all right, then I will switch to the second bit. So after that, we list all the atoms. We need to describe what are the gluing rules among these atoms to find, to produce the generalization of the quiver. So again, as in the Lagrangian setup, we have many building blocks that are indecomposable, and then the operation that glues them together to give a molecule, namely the generic theory in the class that we are studying, is gauging of a flavor symmetry. Okay, above again, we have a pictorial description of the Calabi-Yau threefold, where again, lines above, in the part above the figure, correspond to non-isolated singularity within the Calabi-Yau threefold. And as before, like for example, the black line on the left intersect the blue line on the left at the point that I denoted with xi. And similarly happens with the black lines on the right that intersect the blue line on the right at the point xj. Well, these, via what we said in the previous slide, they can be pictorially represented by these generalized bifundamentals that are interacting superconformal field theories that display a G times G flavor symmetry. Now, what is the geometric analogous of gauging a global symmetry? Well, the gauging operation is the one described below. So you want to glue together the blue nodes into a single round-shaped gauge nodes and gauge the diagonal combination of these flavor symmetries. And these, we will see, correspond geometrically to join the two blue lines above in such a way to form a compact line within the Calabi-Yau threefold. Sorry, disclaimer is that whenever I say line today, really I'm thinking of geometrically as working over the complex numbers. So these lines have actually real dimension 2, are isomorphic to C, to the complex numbers. Okay. And so this ends the motivation, strategy, and the presentation of the problem part. Is there any questions so far? Okay. So now I can get more technical and talk about the bits about indecomposable building blocks that are these conformal matter atoms. Okay. So again, we want to consider these double line bifundamentals that, well, double lines means that these are actually non-Lagrangian theories that are strongly interacting. And I define them as the following system of equations. So I have 3 variables x1, x2, and x3, and 2 variables below u and v, okay? And I is one among 1, 2, and 3. So overall, we have 5 variables, 2 equations. This is all complex variable and all equations are complex. And so this is defined for us something that has a complex dimension 3. And one can check that is actually a Calabi-Yau threefold. The first equation is the polynomial equation defined for us. So the first equation, if I just look at the first equation, has just 3 variables, and this one complex equation. So just looking at the first equation, I get a Calabi-Yau twofold that indeed is labeled by this G that is of an ideal algebra. So this equation, the first equation will be the equation of a certain dual singularity. Let's do an example to be more concrete. If I take G to be A to J plus 1, and we study this particular atom, then the first equation gets this particular shape. Okay, yes, sorry, this is a typo, should be A to J plus 2 below. Okay. This is a polynomial equation that actually can be shown to define the A to J plus 1 AD singularity. Okay, this presentation with 2 equations in this particular case is cumbersome. We can actually sell the second equation to replace x1 everywhere with the combination u times v. And so we can think of it also equivalently as a single equation. In C4, it's just a matter of presentation, but I will need actually both the presentation. They will be more useful in different occasions. So let's now describe the singularity structure of this Calabi-Yau threefold. And we want to see that actually produce what we want from our Calabi-Yau threefold. Namely, the singularities must be non-isolated. There must be two described by two complex one-dimensional loci that are the blue and the black ones in the figure, that they have to intersect at a single point, and on a generic point of the black or blue lines, the singularity must be of A2J plus 1 type. Okay, so for example, let me fix in this equation on the right u to a certain specific value u0 different from 0. Say that for simplicity we can fix it to 1. And so if we look at the equation on the right here, this is just v squared minus x2 squared plus x3 to j plus 1 equal to 0. But this is, again, exactly of the shape of an AD singularity equation. Just describes in terms of the variable v, x2, and x3. Okay, so we discover that if we fix u to a generic value different from 0, we can always play this trick, and we always find a to j plus 1 singularity. And by the symmetry of the equation, this can be also done fixing v to a certain specific value. So fixing u to a certain specific value that we can choose as we want describes, accordingly to the choice of u, the black lines. While instead fixing v to a specific value describes the blue line. And as you notice, I was very careful in saying, oh, well, we have to pick such values to be different from 0. Why? Because at the intersection of these two lines, namely u equal to v equal to 0, and one sees that also has to put all the xi equal to 0, what I said is not true anymore. You cannot say that the local structure of the singularity is the one of a surface singularity times C. And indeed, there is where something interesting happens, and the 5-dimensional superconformal field theory localized. So in some sense, we are happy because, well, we found a threefold that actually has the desired properties, namely these two intersecting lines of dual singularity that intersect at a point where the 5-dimensional superconformal field theory localizes. Okay. Okay, good. So now I want to highlight a second feature of this Calabi-Yau threefold that will be very relevant from now on. Namely, we find this symmetry acting on the zero locus of these equations. I can rescale u times by a factor of lambda, where lambda is a non-zero complex number in C star, and we can instead divide v by lambda, while leaving the axis untouched. And wherever x1 is different from 0, well, this describes for us a C star submanifold embedded inside the Calabi-Yau threefold by varying lambda. So we can say that actually a threefold is a C star fiber. And since x1, x2, and 3 are untouched by the sister action, and they satisfy the first equation, that is exactly the equation of the a to j plus 1, then we can pictorially and also quantitatively describe the Calabi-Yau threefold X with this commutative diagram. Namely, we have a fibration of C star. The Calabi-Yau threefold can be thought as a fibration of C star on C2 mod Z2J plus 2. Okay, because this C2 mod 2J plus 2 is exactly the zero locus of the first equation. Now, this is a good news, actually, because there exists, whenever we have a C-star fibration, there exists what is called the type 2 ACN limit. So we can take a small value for the string coupling, then, sorry, a small, we can reduce along this C-star in order to get type 2A on a certain Calabi-Yau twofold fibered over a real line with some D6 branes wrapped on some cycles, on some 2 cycles of this Calabi-Yau twofold. Just the point is that this limit is well understood when the basis of this star fibration, that eventually will be the type 2A geometry, is smooth. So the first thing to do is modifying this threefold by some blow-ups in such a way to have a star fibration not anymore over a singular AD singularity, but over a resolved AD singularity. And in particular, this, at the differentiation loci of this map, whenever I cannot play this game of rescaling u and v by a factor lambda, at this loci we will find some d6 wrapped on 2 cycle, and the theory governing d6 will turn out to be Lagrangian. Let's see how. So first of all, to perform the resolution, I have to perform the usual resolution of the Duval singularity of type A to J plus 1, that it can be described by this in terms of historic variables from Z1 to E1, E2, E2J plus 1, and Z2. Whereas usual, the 2 cycles of the resolved Duval singularity are associated to, are obtained by putting to 0 these variables. This actually might seem to be very many variables, but we have to identify them by some sister action. So just the sister vector whose action, this sister action are the rows of the matrix on the top right of the screen. And the important bit is that if I set, for example, Z1 equal to 0, sorry, I get, I'm considering a certain non-compact 2 cycle within the Duval singularity. E1 equal to 0, I'm considering a certain 2 sphere, and so on. And this compact 2 sphere intersects, one can read them from the toric diagram, as the A to J plus 1 Dinkin diagram. However, we are not dealing just with Duval singularity. So as you can see before, we had the 2 equations. The first one, in some sense, disappeared because, as we will see, is automatically parameterized in the correct way by the Z, and the E is automatically satisfied. We don't have to insert it anymore, but we remain with the second equation. Why? Because performing the blowdown actually is equivalent to give a dependence of the variable x1, x2, and x3 from the variable z and e. Okay, and so the equation that we see above is simply the second equation of our system of equations, written once we evaluate x1 equal to x1 of z1, ei, and z2. And in this particular case that we choose, this equation has this shape. So I have E1 and E2J plus 1 to the power of 1. Then I have another block with the power of 2, and so on. Now, we are looking, we want to understand, okay, in this type 2 geometry, the interesting bits is brought by the D6 branes. And this equation is telling us where the D6 brane sits. So for example, the fact that we have E1 to the power of 1 is telling us that there is a single D6 branes wrapped over the two spheres described by E1 equal to 0. E2j plus 1 equal to 0 appears with E2j plus 1 appears with power 1, so there is a single D6 over a cycle described by setting to 0 E2j plus 1. Instead, if I set to 0 E2, I have two D6 branes, and so on and so forth for all this expression. And this permits me to write down a certain quiver that where the yellow nodes can be thought as the two cycles of the AD singularity wrapped by the D6 branes. So for example, the one on the left corresponds to E1 equal to 0. And we see that there is a single D6 because in the equation above, E1 appears with exponent 1. Going on the right, we see there is a number 2 because E2 appears with exponent 2. And at the J position in this quiver, we see J plus 1 because this EJ appears with the red exponent J plus 1. Finally, this factor of Q squared is associated to non-compact D6 branes. And since it's squared, one can show that the intersection of this factor with the rest of the D6 branes happens exactly on the central stack of D6 branes. And so we can draw the following picture. But the following one is much more than a simple picture that describes us where the D6 branes are wrapped on the type 2A, in type 2A. Because we know from string theory that when we have such a D6 brane wrapped in this way, then the theory that governs low energy D6 branes is Lagrangian quiver gauge theories. And so we can think of this graph that I just draw not just a picture that shows us where the D6 branes are, but actually as a quiver that describes a 5D n equal to 1 Lagrangian theory that for sure cannot be super conformal, but should be thought as a mass deformation of the superconformal fixed point from which we start. Because in the geometric engineering setup, mass deformation corresponds to resolution, to some kind of resolution of the singularities. Now, there is a first good news that this Lagrangian quiver in 5D, and there are techniques by a paper of Yonekura that permits to, via instanton counting in 5D, to understand what is the flavor symmetry in the UV, at least part of it. And the result is that in the UV, the flavor symmetry in this case is at least, or with this kind of quiver, is at least of type A2J plus 1 squared. And so we are happy because we double check the prediction from geometry. Since we have two lines of A2J plus 1 singularities intersecting at a point, geometric engineering will tell us that we are expecting to find such flavor group. And this is double checked by this mass deformation of the theory. Okay. Is there any question so far on this one? Okay. So now I will make use of this Lagrangian description to present one of the results that we got in the paper of today with Julius Grimminger, Michele Risotto, and Andrea San Giovanni. So this Lagrangian phase of the 5D superconformal field theory, this Lagrangian, this mass deformation that flows to this Lagrangian phase, permits us to easily write down a certain peak web in type 2B that produces exactly this kind of Lagrangian quiver in 5 dimensions. And the result is the one here below. Now, what we can do is that with the peak web technology, we can easily go to the infinite coupling of this quiver that will correspond to the UV CFT. Doing that, we obtain the following brane setup. And this is very good because the infinite coupling brane setup permits us to understand a lot of the dynamic of this conformal fixed point. In particular, we can read what is called the magnetic quiver. So on the left, we have the infinite coupling peak web. And we can, by standard technique by now, red the magnetic quiver of this 5-dimensional superconformal field theory, that is a 3D n equal to 2 quiver, 3D n equal to 4 quiver, whose column branch is isomorphic to the X branch of the 5-dimensional superconformal field theory. And we get the result on the right. So please note that on the right we have the nodes correspond to, on the right I'm drawing here a quiver, a 3D quiver, whose nodes are of type UN. While on the left, there is a pictorial representation of of a 5-brain web, in which the dots instead correspond to 7 brains. We exit from the screen. Okay. The nice bit is that these techniques permit us to quantitatively study the X branch of this 5-dimensional superconformal field theory, and also of their lower dimensional descendants, for example, the 4-dimensional superconformal field theory. Because X branch is invariant by circle reduction, if I do standard circle reduction. And this, together with counting of the column branch dimension, permit us to conclude that the 4-dimensional colportification as a byproduct of this analysis, that per se is interesting because we are characterizing the 5D CFT which we are interested in, as a big product, say as a corollary, we know that the circle reduction of these 5-dimensional conformal matter atoms, so these indecomposable blocks that we obtain from geometric engineering, is a theory of class S type. Why? Because the magnetic quiver is exactly of class S type, and also we can double check the dimension of the Coulomb branch. Okay, very good. And this concludes the section on conformal matter atoms. But I hope it wasn't too technical. Maybe you can, is there any questions so far on what I showed?
Yeah, Mario, could you just remind me what a class S magnetic quiver is?
Yeah. Okay. Going back, so at least I will restrict the better statement that I should have done is that this theory is, this specific one is a class S theory with regular punctures. And this is obtained as usually this star shape, this shape that is called star shape. And this one usually defines by, in a work of Benini, Xie, Tachikawa, three-dimensional theories that are called Tirot, and these are ascending quiver with, in this specific case of type U. And each of them have also a SUN type flavor node. These correspond to the puncture of regular puncture in SUN 2,0 class S construction, and then one gauge the diagonal combination of these flavor SUN nodes to get such quiver. So yes, the central node here can be thought as a SUN node, while all the others are unitary. And actually, the two description matches because we can always decouple a diagonal U1 from the quiver, and this corresponds to make the central node of the SUN type. But yes, this typical star shape of the magnetic quiver is for class S theories.
Very great. Thank you.
Thank you. Thank you very much. Okay, so let's go on and let's talk about 5D conformal matter molecules instead. So by molecules, I mean all the possible gluings of atoms, really in exact analogy with chemistry, that I don't know actually, but very well. But okay, we have our bunch of the indecomposable building blocks that are the atoms, and we can glue them together via gauging. So now that we listed the specific kind of atoms in the previous section, now I'm going to talk about how to glue them together to make molecules. And okay, I anticipate these. Maybe somebody will wonder why I'm just talking about atoms of A to J plus 1 type. Well, that's just for the reason of exposition, but for sure we were interested, and indeed in the paper appear, and we focus mainly on atoms of type D and D. I will come back to that at the end of the seminar. Okay. So now let's talk about molecules again. I remind you of the geometric construction. So above, we have again the pictorial description of the singular locus of the Calabi-Yau threefold. And we have two copies of them. So there is this black line and blue line that intersect at the red point on the left xi. And similarly on the right, top right, we have a blue line and a black line that intersect at the point xj. And if the two lines are not the blue lines are not identified, these can be pictorially represented as we did in the previous section with these generalized bifundamental that crucially are also labeled by this label I or J. That is telling us how the two lines of dual singularity intersect. Very good. Now we want to gauge together a diagonal combination of the flavor symmetry represented by the blue square nodes. And so to do so, we can compactify the blue line. Okay. So on top, let's do again. Like on top, we simply like join the line with this dashed line, and this compactify the blue line. And on the bottom of the slide, we gauge together these flavor groups in order to get a gauge group of type G, where interestingly G can be whatever kind of a singularity, E6, E7, E8, and so on. Okay. And we can iterate these in order to create the most generalized quiver. The first interesting bit is that one actually discovers that such generalized quiver can just assume a linear shape. They can be generalized quiver, but just a linear generalized quiver. So if we force the gauge nodes to be of a fancy AD type, for example, G equal to E6, E7, or E8, then the only possibility we have for building a generalized quiver is having a line of these generalized gauge nodes. And say that, for example, I want to make N1 nodes of type 1 and 2 nodes that comes from collision of type 2, and then N3 nodes that come from collision of type 3. And this collision type is decided by the second equation of the system of equations that I showed before. So maybe it's going to appear. Yes. Let's go back 1 second. So if you remember, for example, here, let me show here what is more clear. Okay, here, the system of equations that defines the singularity for us as a first position, always the ideal singularity that we want to choose. But the second equation is uv equal to one of the possible coordinates appearing in the first equation. And so, which choice I do is gives a different superconformal field theory. And so the choice xi exactly is telling us that in this system equation, I'm taking, for example, x1, x2, or x3, or also any linear combination of them. That's also another possibility. Okay. So the important thing is that now we find ourselves with this generalized quiver that, as we saw in the previous slide, amounts to gluing together some blue lines of AD singularities into some compact lines. So now each glue lines, namely each gauge nodes in the generalized quiver, each round shape node in the generalized quiver, correspond to a compact to sphere, a compact P1 within the Calabi-Yau threefold. So, for example, in the quiver above, we can say that we have N1 two spheres supporting that are associated to collision of G-type dual singularities, and the collision is of type 1. We have N2 of type 2 collision and N3 collision of type 3. But in any case, the very important bit is that we have some compact curves within our Calabi-Yau threefold. This is telling us that we are not at the most singular phase, because whenever I have something compact in a Calabi-Yau threefold, I can contract it and go to a more singular phase. Okay, up to technicalities, but this is the idea. I cannot always contract curves, but okay, up to technicalities, every time we see, for example, two sphere within the Calabi-Yau threefold, it's a good idea to contract it, because this introduces a scale that brings us away from the conformal fixed point. In any case, so we see many compact curves and many compact two spheres, and we contract them. the nice bit of this blowdown of this geometric operation is that actually is in some sense mild, because the first equation that tells us what are the kind of dual singularities that collide at each collision point is untouched. It's exactly as for the atoms. And the second equation also is mainly untouched, but there is just this red modification on the right-hand side. For example, the atoms in particular can be recovered setting n1 equal to 1 and n2 and n3 equal to 0. And this gives the atom of type 1, the atom of type 2 similarly, and so on. But let me first comment on two things. So the first bit is that, the main thing that I want to comment on is that we can again reach a Lagrangian phase. Why? Because the first equation is untouched. And the second equation again displays this nice C-star symmetry that permit to say that again this threefold is a C-star vibration over an AD singularity of type G. So this structure were not ruined by the fact of gauging together many conformal matter atoms. It's still present. So we again have, for the same type 2A limit, Lagrangian phase described by a G shaped with G that E singularity we started with. So for example, for here I'm describing again the A2J plus 1 example, but if we started from an A6 singularity, it will be an A6 shaped King dagger. In any case, we still have this infrared Lagrangian description of the singularity. And the data of this N1, N2, N3 in this phase just modify the rank of the gauge nodes. So if you remember, the whole quiver has occupation number 1, 2, and so on. Well, instead, this quiver has 2, 4, a flavor node of type SU4, and instead before we have a flavor node of type SU2. And the reason is that here I'm showing the diagonal gauging, the gluings of two atoms of A2J plus 1 singularities of the same type. And this fact that there are two of them duplicates the rank of the group of the nodes in the gauge group of the Lagrangian phase. Okay. And again, one of the most useful features of this Lagrangian phase is that we can use it to get the Pick-Weber realization. So if one plays again the same trick that I show for the atoms and goes in the Pick-Weber to the infinite coupling limit for many conformal matter molecules, in this case I'm showing the A case in which we just take atoms of type 1 and atoms of times 1, we get this infinite coupling Pick-Weber, and from that we can read the magnetic quiver of the infinite coupling point. And the first surprise that appears that this infinite coupling magnetic quiver is not of class S type. So, since the Higgs branch is preserved by circle reduction to 4D, this is telling us that if I take the 5D conformal matter molecule, I go to the infinite coupling limit in the 5-dimensional space of parameter, namely the extended Coulomb branch, and then I reduce on a circle, I land on a 4-dimensional theory that displays the same flavor symmetry, so of type, for example, G squared, with, I don't know, in this case, we will be A2J plus 1 times A2J plus 1, but it can be E6 times E6 or SO2K times SO2K. But this theory that we are discovering is not a class S theory. And so, in some sense, this is one of the nice output of this that we are starting to see of this work. Because on top of describing the dynamics of the 5-dimensional theory, we are also, for free, discovering new 4-dimensional unequal to 2 theories that displays nice features and are in general not of class S type. So let me see more precisely what is class S and what is not class Fs. So we find that the conformal matter atoms that introduced in the first part of the seminar are class S or class S type, and they have 3 regular punctures, 2 being the maximal ones, the full punctures, And a third function that is decided by the precise type of collision whether it is chosen. Like, for example, if I took uv equal to x1, it will be a certain kind of puncture, and so on. Equal to x3 will be a different kind of puncture. Then the temptation is when we get to the generalized quiver phase, that is the beginning of these slides, but with still these 2 cycles inflated. So not at the most singular point. We check also with the magnetic quiver techniques and computing the Calabi-Yau dimensions that the result is what one naturally expects, in the sense that we are gauging the G-type flavor symmetry supported that in 5D means compactifying lines of reverse singularity. In 4D means that we are gluing together along a maximal puncture many of these triskelion, many of these fixtures, and the result is the one that I show here below. The interesting bit is that this is not the most interesting theory that we can get from circle reduction from 5D, because it's not like the theory corresponding to the interacting fixed point in 5D. And one of the future lecture is using this magnetic quiver that we computed for the infinite coupling point in 5D, guess what is the 4-dimensional n equal to 2 corresponding theory. Okay, so let me do a recap of the result that I presented so far, and also a more broad recap of the result that we found, but I was not able to explain today because it was more easy to explain the A case. The other introduced more technicalities. So first of all, we are able to construct atoms and molecules that for any AD type Lie algebra that I denoted always with G. And so these are interacting 5-dimensional superconformal field theories with gauge group, with flavor group at least of type G times G. So we get it E8 type E8 and of many type and so on, dk times dk with k arbitrarily large. And okay, we find many atoms that seems to be more intrinsic of 5D. And so one of the open questions also to understanding the higher dimensional origin of them, which of them they descend from 6D, and if they descend from 6D, what is the precise mechanism? The second bit is that, as I showed before, the generalized quiver always admits a Lagrangian quiver phase. And so we can say that in the language saying that we found a new UV ultraviolet duality in 5 dimensions. That says that the same superconformal field theory, that is a conformal matter molecule, admits two kinds of mass deformation. The first is into a generalized Lagrangian linear quiver, okay? So that was the one I showed in 2 slides before. This one, sorry. Where the edges are not Lagrangian, are conformal matter atoms. But this theory also, the superconformal point of this theory also admits a mass deformation to a Lagrangian field theory that is a quiver of type with nodes of type SU, and this is shaped as G. So until now, I always show quiver shaped as a 2J+1, but we can also have a quiver with SUN node shaped, for example, as the E8 linking diagram. So one of the main results of the paper of today is that for G of type A or D, we give in the paper of today with Del Zotto, Grimminger, and San Giovanni the Pico-Weber realization of the atoms and of the molecules. And we are able to extract the infinite coupling magnetic quiver, so having a grasp on, we can study at this point from like what point, and it will be a follow-up to study, for example, the Hilbert series, the asset diagram of the X branch of the 5-dimensional superconformal field theory, and so on. And for the E case, well, we don't have a Pico-Weber realization, but we can again show that 4-dimensional reduction is of class S type, because we can match the column branch dimension, the X branch dimension, and also the flavor symmetry. And also this resonates with an analogous construction by Omori, Shimizu, Yonekura, and Tachikawa that did an analogous construction from 6D to 4D. Again, the reduction to 4D has two maximal puncture and a third puncture that is determined by the selected Calabi-Yau threefold. Okay, the last bits about what we learn about the four-dimensional reduction of these five-dimensional conformal matter atoms is that and molecules is that atoms and generalized quiver phase of molecules reduced to class S theories for any G, also for G 678 or D. And instead, the 4D reduction of the 5D molecule CFT at infinite coupling, namely I shrinks of all the two spheres appearing associated to the generalized quiver phase, is not of class S type. And so we are discovering new kind of interesting four-dimensional equal to two theories that we can also characterize because, and this is part of a possible follow-up, that we're doing that is to characterize what are exactly these four-dimensional theories. Okay, so we arrive at this point, and so now, if there are no questions so far, I can very briefly tells you about an appetizer about these works on trinions and tetrons. Namely, instead of looking for bifundamental of with D time D flavor symmetry or E time E flavor symmetry, we search for something like with D cube flavor symmetry or D to the power of 4, and then conclude quickly with the follow-up that we are currently investigating. Is there any questions so far? Okay, so I will now briefly tell you about the trinion and the tetron. So similar to the bifundamental case, we can also collide three lines of decay type singularities. And the theory that we obtain, we expect to have a flavor group at least of type decay to the cube, so SO to K cube flavor symmetry. And in the current work with Michele Del Zotto, Michele Graffeo, that is a mathematician at SISSA, Trieste, and Andrea San Giovanni, we are uncovering the fact that actually in M theory, we can have this collision of three lines of dual singularity of type D at a single point. And so actually there exist and seem to be Calabi-Yau, they are Calabi-Yau, these manifolds. And so they seem to exist in 5 dimension theories with a Fravor group, such trivalent Fravor group. Actually, we can even do more, because we can also find collision of 4 lines of type D with particularly fine tuning. And so an ongoing work with Del Zotto, Graffeo, and San Giovanni is to see whether also this theory admit an infrared Lagrangian phase at weak coupling, can be deformed to a weakly coupling Lagrangian, and also what are the gluing rules among these trinions and tetrons, or among one of such trinions or tetrons, and an atom, for example, who those that I show in the previous slides. Okay, so let me conclude with our giving an appetizer of the current direction of investigation. So first of all, we would like to systematically study and list all the bifundamental with a G-shaped Lagrangian quiver phase that admits such G-shaped Lagrangian quiver phase with the gauge group of type SU. This is important. And this is an ongoing work with Antoine Bourget, Michele Del Zotto, Julius Grimminger, and Andrea San Giovanni. Then we would like to uncover the relation with 6D and 4D superconformal field theories. And something that is, so in some sense, in 4D I already showed more or less during the seminar what is the thing that we want to achieve. We found the new 4D equal to 2 theories that has a interesting flavor symmetry, like E6 times E6, but they are not of class S type. And so, guided from some data that are preserved from going to from 5D to 4D, we would like to characterize and understand what kind of theories are they. And this, again, one of the current investigation that we are doing. But even more interesting probably is the relation with 6D. So since there is in 6 dimension the classification of 1,0 theories, and there was the conjecture there was the conjecture that I mentioned at the beginning that states that all 5-dimensional equal to 1 theories can be obtained from circle reduction of a 6D 1,0 superconformal field theory or little string theory. Given this conjecture, it's interesting to this give a motivation on our work, because we would like to find counterexample to this same statement. And in some sense, this 3% tetron seems to be in tension with this statement, because in 6D instead, in 1,0, we don't have such trivalent junctions. And indeed, yes, that's prohibited in 6D because the class of Calabi-Yau trifold that we can use for FT or geometry engineering is more constrained. We need to use elliptically favored Calabi-Yau trifold. Instead, in M theory, we can also have no elliptic fibration at all. So we are more free, we are more Calabi-Yau at our disposal. And so the big question is that this theory that seems to come from non-elliptically fiber Calabi-Yau trifold, do they admit a 6-dimensional origin? And this is interesting because, well, in 6D, the corner of 1,0 theories that are in principle allowed by anomaly cancellation and so on and that cannot be realized by F theory is very small. And I think that also there is a paper by Lakshbar in which the author says that actually there is none. And so in 6D, one will say that all the 1,0 superconformal field theory descend and can be coupled to an higher dimensional supergravity theory that in that case is non-perturbative type 2B. And so the question is there anything similar also in 5D? And these amounts to understand what is the relation between the 6D theories and the 5-dimensional one. And finally, another direction that we are trying to investigate is how to match the magnetic quiver analysis of our trifold in order to with the complex deformation of the Calabi-Yau trifold in order to find a good dictionary between the two pictures, because in some sense Calabi-Yau trifold seems to be more general, but they are also less understood. With respect, the dynamics is less understood with respect to PQ webs. Okay, so thank you very much for your attention, and okay.